All right, hey everybody, Mr. Fortin coming at you unmasked. I'm the only one in this room here at your favorite school, Lowell High School. Anyways, I'm going to film this video right now going through these problems 573, 574, 575. And if you're good, I might do problem 577, which is your one homework problem. Okay, again, got to finish the classwork, right? We're not gonna let you do this classwork tomorrow. But I'm filming this video because we had that fire drill today, right? Which took up 20 minutes of both classes, right? We got started late, third block, and we ended early, second block. So anyways, I said to a few people I'd film video going through these problems, which you have to do in case you're having a little bit of trouble making sense of these recursive, right? Recursive equations. And that's what we start with here on the first one here, is that we're given a recursive equation, okay? So one of the things I try to emphasize in class is that when you have to write a recursive equation, is that it's actually two equations, right? We have two equal signs. We have an equal sign here, we have an equal sign there. Okay, so it's actually two equations you have to write. Okay, and in tandem, they kind of allow you to generate a sequence, come up with the terms of a sequence here. And that's what we're going to do in question one, is help Colin write the first two terms of the sequence. 1, 2, 3, 4. And I know I went through this in class. I'm still going to go over it again right now. The way I would read this right now is you always got to start with what one of the terms are. Okay, what one of the terms are. So here, I basically have two equations. Okay, this one tells me one thing, that term number one is 3. The actual term value is 3. So I can put the 3 right there. Okay, I can put the 3 right there. Okay, my second equation is going to tell me what my pattern is. Okay, pattern is. So I take that term number 3, right, which we could consider this term number 3 to be the third term here. This is my current term. To get my next term, right, here. So if I take this term number 1 here, which is 3, okay, let's say that this is my current term. I want to get what my next term is. So what my next term is, t of n plus 1, okay? So if I consider my t of n to be 3, right, term number 1 is 3, t of n plus 1, right, my next term, right, that would be term 2, right, term 2. So I'm trying to get position 2. If I know what position 1 is, right, term number 1 is 3, what am I going to do? The pattern is I'm going to square the current term, okay, t of n, and just square it up, okay, and then what do I have to do? Then subtract 1. Okay, so what do? I square the current term. My current term is 3. I want to get the next term, right? Square it, square 3, I get 9. 3 times 3 is 9, and then I got to subtract 1. 3 times 3 is 9. 3 squared is 9. Subtract 1, I get 8. I get 8 for my t of n plus 1, okay? So now that this is my current term here, term 2, right? T of 2, which is equal to 8. What do I got to do? I got to square it and subtract by 1. What's 8 squared? 8 squared is 64, right? 8 times 8 is 64. You do it in calculator real quick. Hopefully you do that in your heads real quick. Multiplication tables are very important. 8 times 8 is 64. Subtract 1, 63 is my third term, okay? You get the pattern here? Pattern is square the current term. So now that I have this term, right, recursive, right, recurring means happening again and again. This pattern just keeps happening, right, keeps happening here. So if I take 63, now I definitely need to go to my calculator, because a teacher's never presented me with a multiplication table that had 63 as one of the factors. So I'm going to do 63. I'm going to square it up. Oop, I get 3969. It's not that. I get to subtract 1 from it. Okay, wait, is that right? 63? I feel like that number was off. 63, square it. Oh, there it is. It's right. Subtract 1, and I get myself my fourth term, which is 3968. And there are my first 4 terms. Okay, so quick reminders. In order to write a recursive equation, you need to tell the person write one equation that tells you what one of the term values are. It's term value of 3, and that's term number 1. So that here, term number 1 is 3. And then what do you do to get term 2, for instance? Well, you figure out what term 1 is, you square it, you subtract 1. What's the recursive pattern, the recurring pattern here, okay? Is Avery's sequence arithmetic, geometric, or some kind of other sequence? How do you know? And the answer here is other. Why? Okay, because, right, it doesn't have a common difference. So it's not arithmetic or a common multiplier. Okay, you have to listen to my words to figure out what I'm writing, because my words are hopefully a little more clear than what I've written out here. Okay, other. doesn't have a common difference or a common multiplier. If it has a common difference, right, if I'm adding the same amount, so add 5 again, we'll know it, that would be 13, not 63. Then it would be arithmetic, okay? If it has a common multiplier, like 3 times about 2 and a third, right? Like something like that. A little over 2 would get you to 8. Okay, 3 times about 2 would get you 8, but 8 times a little over 2 would only get you like kind of between 16 and 20. Wouldn't get you all the way to 63, right? And 63 times 2 is not even close to 3968. So it's not geometric, it's not arithmetic. And if you're wondering, is this actually quadratic because we're squaring something? No, it's actually not quadratic either. It doesn't follow a quadratic pattern. And I explained that in class. You don't need to worry about it now. Okay, describe, Colin, to how we find the 10th term in the sequence. You do not need to actually find the 10th term, okay? Repeat pattern. Okay, repeat pattern until 9th term, right? Once you get the 9th term, okay, then what you would do is to get t of 10, what you need to know is what t of 9. You need to know what the 9th term is. You'd square it and subtract 1 from. Okay, that's what you'd have to do. So if you knew what the 9th term was, square. You're not squaring 9. You'd square whatever that 9th term is. It'd probably be a pretty big number. Square it, and then you subtract 1 from it. That's what the 10th term of that sequence is here. Okay? This one here, 574. Let's go through it real quick. I'm not crazy about the color that I've chosen, so I'm going to switch to maybe blue. Avery and Colin, they're still at it. Avery, Colin, Trixie, they love these sequences here. Remember Trixie from Friday's class? Trixie's the best. Okay, Colin wrote this. T of 2 equals 19. T of n plus 1 equals T of n minus 2, okay? So let's maybe break down what the pattern is. Remember, we got two things. We have a pattern equation, right? Recurring pattern. Let's say recurring pattern for a recurring recursive sequence, okay? Recurring pattern, and then I also have a term equation, okay? So term 2 is 19, okay? That's easy enough. My second term is 19 right here, okay? And then reminders on the pattern equation is what this is telling me is my current term. I take away 2 from it. That's going to tell me what? Well, what's t of n plus 1? Well, that's going to be my next term of the sequence. Okay, so my second term here is 19. Okay, and then that means I'm going to have 2 terms before it as I'm writing out my sequence. Remember, sequences are comma separated, just discrete values here. Second term is 19, so I put that in the wrong position. Oops. And then in the third term place. So my second term is 19. Okay, my third term is going to be, well, take away 2 is going to be 17. Fourth term, 15. Okay, first term, well, if I'm going minus 2 as my terms get bigger, if my terms got smaller, if I went backwards, this would have to be 21. Okay, that's my first term right there. Help baby write an explicit equation. Is the sequence arithmetic, geometric, or neither? Well, my explicit equation, okay, remember, recursive equations are, tell me what one of the term values are, write it, right? T of 1 equals 3, the first term is 3. And then tell me the pattern, right? Tell me the pattern to apply. Well, to get the next term, you square the first term and subtract 1. That's not a problem. Okay, explicit equations go directly there. Remember, explicit equations are in this form for arithmetic sequences, okay? So it's arithmetic. Okay, arithmetic y, it has a common difference. Okay, common difference of minus 2, subtracting 2 each time the sequence has a new term. The new term's 2 less than the previous term. Okay, it's arithmetic. So if I want to try to come up with an explicit equation, remember that's different than recursive equation. Okay, I got to use what we did last week. I got to use this one that the value of a term, whatever the current term is, let's say, is equal to whatever the common difference is of your arithmetic sequence times by whatever its term number is. Right, whatever its term number is, that's how many common differences have been applied. Right, so my term number here is 4. Okay, that means I've had a minus 2 once, minus 2 twice, a minus 2 3 times. Oh, it's actually a minus 2 4 times if you count what? Term 0, okay? Plus t of 0, okay? So that's your form, okay? To write your equation, all you do is replace what the common difference is, so the number touching n, okay? And I just erased n, what n is right here, okay? The number touching n. Well, what's my common difference? My common difference is minus 2 in this problem, okay? And what's my t of 0? Okay, my t of 0 is at 21. No, t of 0 doesn't actually appear in the sequence itself. T of 0 is your kind of hypothetical y-intercept. You're starting with your initial value. We called it on Friday. So this is plus, well, 23. Okay, if I had one right before 21, 21 is my first term, right? If I had a 0 term, it would be 2 2 higher than this because we're losing 2 each time we have a new sequence, number added sequence. Okay, so it's arithmetic, and there's my equation. Hopefully you got that one. Okay, hopefully did you replace D with the common difference? Did you replace T of 0 with 23? If so, you hopefully got yourself a correct equation. Okay, then Avery wrote this. They wrote T of n equals 6n plus 8. Okay, they're just writing this for a different sequence. Help Colin write a recursive equation. Okay, what do we know about this? Well, we know that this is where my T of 0 is. Okay, so recursive equation. I need 2 things. I need what my one of the terms are. So it could be term 1, it could be term 2. Here, it could even be term 0. It could be the initial value. That doesn't even appear in this sequence, okay? What I know here, this is where my y-intercept goes, okay? So even though a sequence doesn't have a y-intercept, it has that. This is where the y-intercept would be to help us build an explicit equation. To write a recursive equation, we could say that's the 0th term. Take the 0th term, that's 8. And then how do I get my first term? How do I start my sequence? Well, it looks like, oops, 6. 6 is my common difference, okay? So it's arithmetic. That means I'm adding by 6. So 8 is my initial value, but my first term would be 14, right? So try it out. Plug it in. Plug in 1 for n. 6 times 1 is 6, plus 8, well, it's 14. How do we get from 8 to 14? We added 6 to it, okay? There's my common difference, okay? So T of 0 is 8. That's the easiest way to do it, is to do term 0. And then to get the next term, right? To get 0 plus 1 is 1, right? So how do I get term number 1, for instance? Well, I would take the current term, okay, here, 8, and what would I do? I would add 6 to it. Okay, add 6 to it, and there it is. There is your recursive equation, okay? How many equations did I need? I needed 2 equations there, okay? Last question here. I would have loved to have gone through this as a class. If we had those extra 20 minutes, we didn't have the fire drill. We would have been able to go through it, but we got about the Fibonacci sequence. Hopefully, I'll get some things planned about the Fibonacci sequence in tomorrow's class, because it's kind of cool. It comes up in patterns here. Flower petals are often one of the terms of the Fibonacci sequence, and very seldom are they not a term of the Fibonacci sequence. And other things is Fibonacci spiral right here. But anyways, this is the Fibonacci sequence. So here, it's actually 3 equations. Okay, why is it 3 equations? What is it telling us here in the Fibonacci sequence? Well, let's check it out here. Fibonacci sequence, that term 1, or the first term, is 1. Okay, so that's my sequence here. I'm going to write the first 10 terms of the Fibonacci sequence. My term 1 is 1. That's what it's telling me here. It also tells me that term 2 is equal to 1. Okay, so term 2 is equal to 1. And the deal with the Fibonacci sequence that's important, the reason why they need to tell us what 2 of the terms in the Fibonacci sequence are in order to get the recurring pattern going is because if you remembered what we talked about when we did the sequences posters, right? When we arranged all those sequences together, I said which ones went together. The Fibonacci sequence, for those of you who got to the bottom of it, the idea is you take the 2 previous terms, add them together, and that's going to tell you the next term or the current term. Depends how you view what the current term is, or the previous term, or the next term. Anyways, let's see how they wrote it here. Okay, let's check it out. They wrote it, okay, the next term in sequence, right? The next term, my T of n plus 1, whatever my current term is, to get the next term, I take my current term and the term right before it. I call this the previous term. We call this previous term in class here, right? T of n minus 1 would be the previous term, okay? So right now, let's look at it here. They tell us what term 1 and term 2 are. It's 1, it's 1. What about term 3, okay? Well, term 2, let's say that's the current term, term 2. Okay, term 2. My current term is 1, okay? I take my previous term, which is 1, and that's going to tell me what my next term is. 1 plus 1, 2, okay? So T of n plus 1. My next term of the sequence is equal to T of n, okay, which is 1 right here. And then the term before it, T of n minus 1, okay, add them together. That's what's going to tell us the next term of the sequence. So my next term here is 2, okay? Look at this one here. Well, what's the next term? T of n plus 1. Well, the current term here is 2. What's the term right before it? Previous term there is 1. So I need to take 2, the current term, add 1 to it, the one right before it, to get me the next term. It's 3, okay? Here, how about the next one? If this is my next term, this is my current term, that's my previous term. I take the current term. I add it to the previous term. That gives me the next term, 5. This is now the current term. That's the previous term. What tells me, what do I need to do to the next term? I add the current term to the previous term, gives me the next term. This is the Fibonacci sequence. 8 plus 5, 13. 1, 2, 3, 4, 5, 6, 7. We have 7 terms. 13 plus 8, 21. So you're just adding 2 terms together to get the next term, okay? The current term and the one right before. Or we can just call them the 2 previous terms, the ones directly before whatever term we're trying to find, okay? 21 plus 13, 34, okay? Yeah, it's a 21 petal flower. There is. There isn't a 20 petal flower. There isn't a 22 petal flower, I think. I'm not a botanist. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Last one, 34 plus 21, 55. There it is. The first 10 terms of the Fibonacci sequence. Do you want to keep going? You can keep going if you want. Is the Fibonacci sequence arithmetic, geometric, or neither? It is neither. Okay, because it relies on previous terms to generate the next term. It's a purely recursive sequence. Okay, recursive. It's a recurring pattern that it needs to rely upon previous terms to establish what the next terms are. So that's why this writing equations like this way is kind of important to express where the Fibonacci sequence, how we can show it mathematically, rather than just these are the numbers. Okay, describe what you do in order to find the 100th term of the Fibonacci sequence. Okay, what you'd have to do is you have to find the 98th and 99th terms first. 99th is the current term. You add the previous to it, that'd be the 98th term. Add them together. Find the 98th and 99th term. Add them together. And that's what's going to tell you what the 100th term is. Okay, you don't need to find it, though. You don't need to find it. All right, wrapping things up here. And thank you for watching this video. And you're done with your homework if you've done it along with me. I'm trying to go through fast. You can stop and rewatch if you need to. Definitely talking quickly. Okay, so anyways, problem 577. This is your only homework problem, addition, finishing the classwork. So let's go ahead and do it. Write both an explicit equation and a recursive equation for the sequence, okay? I'm going to know that my explicit equation is going to be in this form. T of n is equal to the common difference, okay? Because again, we're just doing arithmetic sequences right now. Common difference times by whatever my term number is, and then I got to add in my initial value, right? My y-intercept. So it's going to be that form. Plus, and that's a t. Looks like a plus sign. It's a little ugly. Okay, recursive equations. Remember, we're going to require 2 equations. T of 1, for instance, equals blank. Well, term 1 is 5. Okay, and then the next term in the sequence, how do I get the next term? Once I know what one term is, how do I get the next term? Well, I take whatever the term is I'm on right now, my current term, and I do what to it? I add what to it? What do I do? I don't know. Okay? All right, so let's break it down, figure out a few things to get our equations here. Well, I know my first term here is 5. Okay, let's do the recursive one first. My first term here is 5. So t of 1 equals 5. There's one of my 2 equations I need. Okay, and then how do I get the next term? What do I do each time this changes? Well, it looks like we're increasing by 3, plus 3 each time. My common difference is 3. So I take my current term and I add 3 to it. Boom. We're done. We're good to go. We got ourselves our recursive equation. What's the recurring pattern? Adding by 3 each time. We need to know it's not just adding by 3 starting at 0. It's adding by 3 starting at 5 as my first term, or 2 as my initial value. Okay, so that's the thing you need to do about here. What appears in the explicit equation is the initial value, the y-intercept, if you will. Okay, so I need to go minus 3 that direction. Okay, and that's going to be 2, right? 2, 5, 8, and then just growing by 3 that way. That's one way you can make sure you found the right initial value. Okay, so my equation here is going to be, initial value here is 2. I already have deduced that my common difference is 3. So it's going to be, put my 3 in for common difference. It's going to be t of n equals 3n plus 2. There's my explicit equation. So let's go ahead and label it recursive and explicit. I already kind of labeled it there, but I'll just rewrite it here. Okay? Message me if you have any questions. Thank you for watching. I enjoy these sequences things. Hopefully you guys are enjoying this chapter here too, or at least viewing equations a little bit differently, and you feel like you're deepening your math understanding of patterns and whatnot. Thanks for watching, guys. Have a great night.